So now let's get to the simulation results. There are various scenarios based on various assumptions, but there are 4 popular scenarios that are often considered and are worth discussing. First, there is the so-called business as usual scenario. You might also know this as the standard run that I already introduced you earlier. So all of the simulations start 1900, they go for 200 years until the end of the 21st century. And as we already discussed, we have a set of finite resources that is slowly but surely depleted. And then we have the agriculture production, so food per capita, industrial output, and population going straight up to a certain point until they collapse. And then there's pollution also going up. So what does this essentially mean? We reach a certain level of luxurious nice living standard that unfortunately is not sustainable because we're using more resources than we have, and we're causing more pollution than we can process, and that at some point then leads to a drop in industrial output, food per capita, and subsequently the population decreases or collapses to a certain point. As I already said, this model is not time sensitive. It doesn't give you a precise date when something is supposed to happen. So if you look at the figure, it is somewhere at the end of the 21st century where problems are supposed to occur, but this is not time sensitive. It is just an indicator that when we continue down this road, this path, then at some point collapse scenarios will occur, which then will cause us quite some problems. But the majority of the problems here are caused by the depletion of natural resources. So for the business as usual 2 scenario, we just assume double the natural resources, because if we had a collapse due to depletion of natural resources, let's see what happens if we double them. And doubling resources could happen, for example, via recycling. If I can use each atom or each part of a certain resource twice because I just recycle them, then I have double the amount of resources. So this is essentially what this scenario looks like. It also accounts for resource depositories that we have not discovered yet. So think about oil, gas, and other stuff. Like every other month or so you can read news that they found a new oil field, or now when we talk about lithium batteries that they now find like new rare earth minerals or lithium deposits that hasn't been known before. So now they have more. So this is essentially what this scenario is supposed to cover. And what you get from those assumptions is, for example, resource-wise, a higher entry level for resources, as a very sharp decline or depletion of those natural resources until the end of the 21st century. And you have a very steep increase when you look at the curves for population, food per capita, and industrial output. They are much steeper than what we have seen in the standard run before. And what you also can see that there is no peak essentially to pollution anymore, and then suddenly it drops, but pollution's going through the roof. So you have so many resources that you use to increase output of the industry so much and increase the population so much that the pollution that you cause is just unbearable, which then causes a collapse of the system. And you can also see that, at least from the model perspective, those drops are much, much deeper than compared to the standard run. The standard run tapers off at the end of the 21st century on a relatively stable level. Those here go almost to zero when it comes to the end of 21st century results. So what the business as usual model represents is more or less a collapse due to pollution. You could also think about climate change equivalent, because climate change hasn't been incorporated in this model yet. Remember 1972? If you look back to the history of political action lecture, you might remember that 1972 was where we slowly started talking about sustainability, caring about the environment, and thinking about climate change. So this is not a variable in that model yet, but the collapse due to pollution is also something that is only supercharged by climate change, because everything that has been considered there for pollution also often contributes to climate change in terms of, for example, CO2 emissions. So business as usual 2 model, still a big problem. Just doubling our resources, e.g. by recycling, doesn't really solve our problem. It seems to rather make this problem more difficult. So, okay, now we're dying due to pollution, either climate change or just normal environmental pollution. What can we do about it? We can try to come up with a lot of technologies to prevent either climate change or pollution. So this scenario then is called comprehensive technology and is essentially the business as usual 2 scenario combined with exceptionally high technological development and adoption rates. So while assuming that we have very frequent technological breakthroughs and that those breakthroughs are also adopted immediately. Why is this important? Because nowadays you might think of the example of battery electric vehicles. And technology is there, but it takes quite a while to be adopted because either the prices are too high or there are some sentiments against that new technology, that some people just like their internal combustion engine cars and favor them over battery electric vehicles, or there is this fear of batteries not lasting long enough and so on and so on. So all of this essentially extends the adoption rate. And for this scenario, we're not only assuming that we have a lot of technological breakthroughs, but also that we more or less adopt them immediately. So two rather bold assumptions here. But would be necessary to combat this pollution problem that we had in the previous model. So what happens if we work with those assumptions? We get a slightly better output result than we had before. We still have a certain resource depletion until the end of the 21st century, but it's still much better than what we had before. And we also still have a certain drop in industrial output and in food production, but the population doesn't seem to collapse because we're somehow able to manage pollution and push it more or less to close to zero by the end of the century, which then allows us to stabilize our population, getting the food per capita back in check, and also at least somehow managing to maintain a certain industrial output. But all of this under the assumption that we have twice as many resources as we are already aware of, that we have super challenging technological breakthroughs, and that we adopt those technologies right away. So 3 rather unrealistic assumptions, but under those assumptions we're slowly but surely getting there. But still there is a certain problem here. It's not quite perfect yet. And this is what leads us to the stabilized world scenario, because what we have in the comprehensive technology scenario is pretty much a problem caused by the rising costs for technology, which then eventually cause some declines. So how could we try to reduce those costs for technology? By pretty much trying to use less, for example. What we're preaching in this lecture again and again, the most sustainable thing you can do is to consume less. But that requires changes in societal values and priorities. To not say, okay, I need 100 iPhones to be happy, but rather like one iPhone or no iPhone can make me happy. That is a change in society values and priorities. And if we assume that on top of the CT scenario, then we get the so-called stabilized world scenario. So double the natural resources, exceptionally high technological developments and adoption rates, and changes in societal values and priorities. And then we get something that looks relatively decent. So we have a sharp increase in population, food per capita, and industrial output, and then it all stabilizes. At the same time, we have at some point a pollution problem, but due to our technological advances, we can handle that. And also our resource depletion very much drops to a stable level by the end of the 21st century. So this sounds to be a nice scenario that is worth considering as a goal for our society. So in summary, if we look at the 4 scenarios, the most popular scenarios, business as usual 2, comprehensive technology, and stabilized world, we obviously would like to achieve a stabilized world scenario, but it is also a very unlikely scenario because all those assumptions require a lot of willpower from us as a society. So if we go back to our earlier definition of sustainability, being able to satisfy our own needs without compromising the needs of future generations, where does the World3 simulations result put us there? So what we've seen for the standard run, but also business as usual too in comprehensive technologies, we are not really approaching a level where we can talk about sustainability. So the World3 model clearly indicates that we are already consuming resources at a faster pace than the planet is able to regrow and generate them. And this was something that they already discovered in 1972. So the standard of living that we are looking for is not sustainable. And relieving the limiting factors is not really a solution. So just doubling the amount of resources led to a problem. Thus, assuming comprehensive technologies as an example is also not going to cut it. And especially doubling the natural resources is, instead of helping the cause, is more an accelerator towards disaster. And preventing the worst case scenario is essentially just possible by reducing consumption. All the other scenarios lead to one sort of collapse, one or another. So comprehensive technology not as severe as the one before, but still a problem. And what we're essentially looking for is the stabilized world scenario. Each and every model has its advantages, but obviously also its disadvantages. And due to its popularity, but also the fact that it's already been around for 50 years, the World3 model in particular has been criticized widely for various reasons. So the model is criticized obviously also by its authors itself, because they have a very critical view on their model. And there's even a complete book dedicated to criticize the model, which is called The Models of Doom, a critique of the limits to growth. And coincidentally, it's even longer than the actual book. And another criticism, before going into the more details, like what the actual criticize, what are the specific parts, is that the original book did not contain the equations governing the World3 model. But they released that 2 years later in a separate book called Dynamics of Growth in a Finite World. And I would like to use this fact actually as a way to motivate and market the book to you, because the original The Limits to Growth books from 1972, as well as the subsequently released updates, are very easy reads. You can nicely read them. There's not too much math involved. It's something that you can read in an afternoon or before going to bed. It's very frustrating and very depressing, but the books itself are not super fancy, complicated academic constructs. They're quite nice reads. So some criticism can also be an advantage. But now going to some of the actual criticism. This is once again not a comprehensive list, but listing the most common but also most relevant criticisms of the model. First of all, it was heavily criticized by economists. The model questions the fairy tale of eternal economic growth. And as we've discussed many, many times before in this lecture, this is somehow difficult in a system with finite resources. Even if we assume that things like the circular economy that we're going to talk about in subsequent lectures, or subparts of the circular economy like recycling, allow us to use resources again and again and again, and potentially even indefinitely using them again and again, at some point we're still running into a problem with respect to where to get resources, where to grow all that stuff, how to handle pollution and other factors. So there is almost no way where in a finite system you can still work with this fairy tale of eternal economic growth, but this doesn't really sit well with the economists, and this is why they don't really like that book. Another more well-founded criticism was based on the fact that they had a lot of aggregated variables. So we did not differentiate between the different types of resources. There's one resource for all the resources we have on this planet. There is one food for all the different food assumptions. There's one pollutant and one population. Those are obviously very, very simplified parameters and aggregated variables. This is why we also talked about the planetary boundaries before, to give you an idea about different types of complexities and what you can draw from different numbers of variables. But even with those simplified variables, you still had those 150 equations governing those different variables. So there is complexity, but also oversimplification, which is one of the other things that the authors have been accused of. So either the model is too complex, or they're criticized for oversimplifying things using something like aggregated variables. And another simplification is that there are no geographic structure, no social distinctions. There's just average food per capita, no matter whether you're living in Europe, in Africa, in South America, or wherever, it's all the same. And there's also a lack of statistical analysis. So what you would assume from such a simulation is that you, for example, have something like the error bars, but all of this does not exist. And finally, something that we already discussed before we got into the results is what I said is like it's 1972. You had problems and difficulties getting the input parameters right because you did not have like Wikipedia to look up the birth rates of every country. You had to get them from somewhere, and then you had to aggregate them. And the quality of data as well as the widespread availability of data wasn't as common as it is right now. So they are not only having those criticisms that we already listed, but also the input information were not as solid as you would have them today. And then you also had to oversimplify a lot due to the very limited amount of computation power and also the ability to overlook those complex systems. So that said, the model gives us relevant output information that we can use to first understand what the future might look like and then take according actions. But there are also various downsides to this model. You could now ask yourself, like, why are we talking about this model if it's that old and that heavily criticized? Because, first of all, it still holds true. Like when you compare the results after 30 or even 40 years, the model is still quite close. You still have Forrester's dilemma that we're quite close to the starting date still, but it gives solid results. And it also doesn't really matter if it's like 5 or 10% off. If the general trajectory, the general trend is still true, we're still in a big, big problem. And this is why this model is still relevant. And it's also simple to comprehend despite its complexity. If we would now look at 500 different specialized simulations for various aspects that the World3 model comprehends in one like system, first of all, we would take a whole lecture to just do that. And also all those 500 models would be way too complicated to simply understand them in a bachelor course. So this is why, or like some of the reasons why this World3 model is still relevant today and why we're talking about this in our lecture. So what's the take-home message of today's lecture? We first briefly talked about planetary boundaries, but for most of the lecture we've been concerned with the World3 model that was published in 1972 as part of the book The Limits to Growth. And the World3 model is built using system dynamics, and the mathematical equations governing the model are written in Dynamo. And the result that we get from the World3 model or the most precious outputs from the World3 model are 4 commonly used scenarios that allow us certain predictions of the future. First, the business as usual model, the business as usual 2 model, the comprehensive technology model, and the stabilized world scenario. And if we compare those scenarios, the stabilized world scenario is essentially what we are looking for to achieve, even though it's very unlikely and highly ambitious to get there. And despite widespread criticism, the overall message of the World3 model still holds. So despite the criticism as well as the age of this model, what it predicts still holds, because we're still on an unsustainable path that will most likely lead to collapse of society if we don't take a sharp turn and turn the ship around.